One of the factors that influence the rate of reaction is concentration. This is an example on the reaction between sodium thiosulfate and sulfuric acid. And as indicated here, 2 molar is a higher concentration as compared to 0.5 molar. And as the concentration of reactant increases, the number of particles per unit volume also increase. With this, the frequency of collision would increase. And this will result in an increase in the frequency of successful collision between the reactant particles. Hence, the time taken for the reaction would decrease to complete the reaction. Thus, the rate of reaction increases. The next factor that would affect rate of reaction is surface area, and this is usually used to describe solid particles. Caster sugar has a smaller size of particle. As for rock sugar, the size of particle is much greater. When the size of particle is smaller, the total surface area exposed is much greater. Thus, the use of caster sugar has greater area of contact between reactant particles, which results in greater number of collision between the particles. Hence, the frequency of effective collision would increase. Hence, the rate of reaction also increases. The next factor involves pressure, and pressure is used to describe gaseous particles only. Based on Boyle's law, volume is inversely proportional to pressure. When a system is compressed, the volume of the system is decreased. As indicated here, the particles are brought closer together. Therefore, the number of particles per unit volume is much greater when the volume is decreased. The pressure of the system will increase as the particles are brought closer together. This results in greater number of collision. Hence, more effective collision will occur per unit time, and eventually the rate of reaction would increase. The next temperature that affects rate of reaction is temperature. When the temperature of a system is increased due to heat being supplied to the reaction, more reactant particles will have energy greater than activation energy. This will result in an increase in kinetic energy of the reactant particles. Thus, the reactant particles will collide more frequent, which results in greater number of successful collision. Hence, the rate of reaction would increase. This could further be explained based on Maxwell-Boltzmann distribution curve, as indicated by this curve. The area under the curve represents number of particles. As for the x-axis, it is involving energy. And this is activation energy, which is the minimum energy required for the reactants to form products. At higher temperature, as indicated by the rate curve, at higher temperature, more particles will have energy greater or equivalent to activation energy. This could be shown by this area under the curve, whereby at higher temperature, the area is a sum of B plus A. Since there's more particle with energy greater than activation energy, this will result in a greater number of particles having higher kinetic energy. As you can see, the curve has shifted to the right. This will cause an increase in the frequency of collision and eventually frequency of effective collision. As the particles collide more frequent, they collide with correct orientation, and there are more particles with energy greater than activation energy, which results in frequency of effective collision to increase, and this causes the rate of reaction to increase at higher temperature. I would want to use this example where carbon dioxide dissolving in water to form carbonic acid. In this scenario, as temperature increases, carbon dioxide gas particle would gain more heat energy. With that, the average kinetic energy of the carbon dioxide particle would increase, and it tend to escape from the liquid body. Hence, the solubility of carbon dioxide gas in water would eventually decrease. This results in a decrease in the dissolution of carbon dioxide gas in water as temperature increases. The next factor that would affect rate of reaction is catalyst. Catalyst provides an alternative pathway with lower activation energy, and with that, it accelerates the reaction rate. It will not be chemically consumed in a reaction, thus left after the reaction. This could be further explained based on enthalpy diagram. The activation energy without a catalyst is much higher as compared to activation energy with a catalyst. When a catalyst is being used, there are more particles with energy greater or equivalent to activation energy. Reactant A reacts with reactant B would form a product, and this requires certain amount of activation energy. So with the presence of catalysts, it requires a shorter time to complete the reaction. There are two types of catalysts. One is a homogeneous catalyst where it has the same physical state as reactants and products, whereas heterogeneous catalyst has different physical conditions as compared to reactant and product. An example of heterogeneous catalyst is the use of iron in Haber process, which is a reaction between hydrogen and nitrogen to produce ammonia gas.